Good morning, class. So today let's first go over homework 6. Oops, put these on. And problem 1 was an extension of the previous homework to reinforce your understanding of EF, the Fermi level, versus doping, and doing it for n-type, which is that we calculated the formula EF is EFI plus KT natural logarithm of ND over NI. So it's kind of a simple formula to remember because if ND equals NI, then the logarithm of 1 is 0, and it becomes EFI. Now, saying that, you have to be a little bit careful because this formula was only derived if ND is much greater than NI, and it just happens to work out that way, that for ND equals NI, it gives the right answer. But anyway, moving on, the problem was for the effective masses the same. And then EFI is equal to E gap over 2. That is the middle of the band gap, setting EV equal to 0 just for convenience. And so we can then write that, and the problem was for a band gap of 1 EV and NI of 10 to the 10th inverse centimeter cubed. So we can then just write that EF is equal to 0.5 in EV plus KT, which of course then has to also be in ND over NI. And for convenience, so you could just plug this in and plot it. For convenience, what I'm going to do is I'm going to define ND as 10 to the x. And you'll see why in a second. So then it's 0.05 or 0.5 plus KT, the logarithm. Okay, so this is then 10 to the x minus 10, right? Because NI is 10 to the 10th. And so 0.5 plus KT times x minus 10 natural logarithm of 10. I'm going to sort of simplify things a little bit here. And that's then 0.5 plus for 300 Kelvin, KT is 0.026, and so multiply that times ln 10, which is about 2.3, we get 0.06 times x minus 10. And I asked you to do it for 300 and 400 Kelvin. For 400 Kelvin, KT is about 0.035, and that works out then to 0.0805. Of course, both of these are in EV. So now we can make our plot, and so what we're going to do is I'm going to put some tick marks here. Looks pretty good. into the 12, into the 13. So you can see kind of the reason why I defined ND as 10 to the x is because then on a log plot, x is linear. And let's put 1 EV here. There's the middle of our band gap. Let's draw E sub C so we can keep track of that. And actually, I should add an 11. That's what I forgot to do. I'm going to change these 11, 12, 13, 14, 15, 16, 17. Okay. Because remember, this formula, because when we did the Ni squared thing, we assumed that N was approximately equal to Nd. And so that's only true if Nd is much greater than Ni. So since Ni is 10 to the 10th, we can sort of start at 10 to the 11th, or x equals 11. So then for 300 Kelvin, let's do 300 Kelvin first. All right. We sort of start here, plugging in 0.06, so that's 0.56. And then 12 is 0.62. So what I'm going to do, let me see if I can make a good plot here, freehand. Pretty close, E sub C. All right. And I'm gonna skip up to 17. So for 300 Kelvin, 17, so that's 17 minus 10 is 7 times 0.06. That would be 0.92. So somewhere around here, so to speak. And it's a straight line, of course. You can draw a straight line. And so basically, this goes 0.62. And you can fill in the rest here. And I stop at 10 to the 17 because then we're at 0.92, which is starting to get close to the conduction band. And remember, for this formula to work, we have to stay a few kT away from the conduction band. kT for 300 Kelvin is 0.026 eV. And so at 9.2, that's 0.08, so that's kind of around 3 or 4 kT. So that's a good place to stop. Okay, so this is for 300 Kelvin. Now for 400 Kelvin, same thing, 10 to the 11, we'll start at 10 to the 11. And so it's just a little bit higher here, 0.5805 EV starting. And I'm going to do the same sort of thing. And basically, at 10 to the 15, 5 times 0.08, you can kind of work it out in your head, works out to 0.9025. And so that's where we kind of have to stop because, that's a few kT. Remember, kT for 400 Kelvin, so that's .035 at 400 Kelvin. And, same thing, I'm just going to draw a straight line here. All right, and so that's 400 Kelvin. And you can fill in the points there. And that's EF. versus ND. So hopefully, that problem really reinforced your understanding of how the Fermi level varies as you change the doping level. Okay, problem 2 was to show that the units of the diffusion length, L, are length. So to do that, we have to start with D. Remember our formula flux is the diffusion coefficient times dP dx, or dN dx, it doesn't matter which one you use. And so diffusion coefficient goes as flux over dP dx. Now remember flux, that's carriers per unit time per unit area. Carriers doesn't have a unit, of course. So this is, I'll start using MKS, seconds meters squared. Carriers per unit time per unit area. And P is 1 over meter cubed, and then meter in the bottom. And so that becomes 1 over second meter squared over 1 over meter to the 4th. And so when you do that, that becomes meter squared per second. So that's the units of D, area per time. All right. Now, L was defined as the square root of d tau. So that goes as the square root of d, which is meter squared per second, times second, or the square root of meter squared, or meter. And so we proved it. So hopefully that little exercise kind of improved your grasp on, when we write down L and D and all these things, what they are. All right, and then 3, along the same lines. Okay, so for 3, I'm going to back up a little bit and do our do our diffusion coefficient thing again. And the way I taught you to do this is that J, right, is EF, or ED dP dx, evaluated at xn. And and the way I taught you to do that, since this goes as e to the minus x minus xn over L, that the simple way to think about it is that it reaches Pn0 at L. And so that's EED. And this is Pn0 e to the, running out of room, I'll just write it over here. Oh. Pn0 e to the EVF over KT. All right, so by now that should be, drummed into you that the at the edge of the depletion region, the injected hole density goes as Pn0, the equilibrium hole density, times the exponent of E times the forward bias over KT. So then this becomes Pn0 e to the EVF over KT minus Pn0. That's delta P, and it does that in L. And you could take the actual derivative of this, okay, and that would be great mathematically. I'm just sort of trying to teach you a shortcut when you look at this, which is that that slope there is equal to just drawing that straight line asymptotically. In any event, it gets us to the J is equal to E d Pn0 over L times e to the E Vf over Kp minus 1, and that's just holes. We do the same thing for electrons and add them together. But the point is that this has to then have the units of current density. So let's show that. So the units, so E d Pn0 over L, so this is coulombs. D from up here is meters squared per second. Pn0, that's carrier density. So that's 1 over volume. Remember, carriers don't have a unit, there's just a number. Over m. So what happens is that those get canceled by all but one of those. So this becomes coulombs per second. Bringing those together over meters squared. Coulombs per second is current. Which is the units of J. Okay, so hopefully that kind of reinforced a few things for you. And let's move on to today's lecture. Okay, so today we're going to start on bipolar junction transistors. And so this is our first, pardon me for a second. So this is our first, what's called three-terminal device, which is basically starting with devices that can be used for amplifiers or logic gates or things like that, because they can have gain. And so let's just get started here. And so we're going to start with what you already know, which are diodes. So I'm going to draw a diode, make it nice and big. And I know we've always been doing P on the left, but we're going to do N on the left. And you'll see the reason, well, the reason why is basically because we're going to do an NPN transistor, and for NPN, the voltages and currents are all positive, so it's sort of easier to start thinking about it. Now, we're going to forward bias this junction, and so we're going to put a, remember your mnemonic. So forward bias is a positive voltage on the P side. And I'm going to call this voltage VBE, which we'll explain in a second. All right, now, you guys know what happens. Okay, what happens is that since it's diode, I have a depletion region on both sides. And if I extend this downward here, now it's N of X because that we're injecting electrons from the N side to the P side. And you know what happens. This basically does this sort of thing here, where this is, I'm going to call N B0. Those of you, for whom this is a review, know the letter B here is referring to the fact that that's the base. But it's the same thing. It's the equilibrium N concentration in this P side. And you know that this value here then is NB0 e to the EVF over KT. Oh, sorry, BE over KT. Okay, now, so far so good, but what we're going to do now is we're going to change this picture because we're going to put another junction over here. And what we're going to do to that junction is we're going to reverse bias it. Now, again, your mnemonic, forward bias means a positive on the P side, so reverse bias means positive on the N side. And we're going to call that VCB. And at this point, I might as well start labeling everything. This is the emitter. This is the base, and this is the collector. And so when you see V sub 2 letters, how you're supposed to interpret that is that that's the voltage of the collector with respect to the base. All right, so just to help with that later on. All right, now. Since okay, so there's a junction here, so there's a depletion region. All right, and what happens is that since this junction is reverse biased, that acts like a vacuum cleaner for those electrons emitted into the base, and so what happens is that if I draw this down, all right, it doesn't do this anymore. It does this. So N sub X changes because I reversed. So basically, it acts like you know, a sink, so to speak, for those injected electrons. And so it's sucking so hard on those electrons that the electron distribution gets pulled down to 0 at the edge of that junction. Okay, and we call this the length X sub B, the length between the two depletion regions. Now, the same thing happens on the other side over here, kind of. So let me bring over here. Let me move that VBE over here. So now this is P of X, the injected hole density in the emitter. And I'm going to purposely draw that lower. All right, so this is now, I'm going to use the term for over here, P E0 for the equilibrium concentration in the emitter. And, well, I kind of made this too long now. What I'm going to do, well, this is sort of illustrative maybe, because that's what would happen if the contact was very, very far. But now what I'm going to do is I'm going to move the contact in closer for the emitter. So I'm shortening the emitter. And what happens is that contact acts like a sink also. So because any injected holes get sucked into that contact, and so that has the effect of making that distribution not do that anymore, but go down like that. And I forgot to label this PE0 e to the EVBE over KT. And those are our injected electron and hole densities on either side. This length is then labeled X sub E. And the fact that these become sort of, now I'm drawing them as straight lines. I'll explain in a little bit that particularly this one is not exactly a straight line, but we can kind of approximate it as a straight line anyway for purposes of calculating the currents. Here I'm going to do a little bit of an aside because it's important to understand how you actually make this thing. So over here I'm just going to draw what this thing really looks like if you make it. So if you take a semiconductor wafer, what you would do is you would fabricate so you would take a N-type wafer, you would put in P, and then you would put in N, like that. And so this is kind of, this picture, you know, that picture is this turned on its side, so to speak. Because this is the emitter, the base, and the collector. And the reason why I'm drawing this is I'm sort of jumping ahead here because we're going to be calculating J. What you're really interested in is I. I'm just pointing out that there's a single area A, which is the area, I could draw it in 3 dimensions, the area of this cross section going forward. It's not that, you know, that would sort of correspond to this over here, which wouldn't make sense. The current flow is all in the vertical direction. So there's a single A for all the current components. So I just wanted to make sure that that's clear before we proceed. All right, and now we can basically calculate these current components. And what I'm going to do is I'm going to draw them. So this one here, I'm going to label JE sub N. Hold on a second. And that's this one here. And so Je sub n is, okay, remember our formula. Okay, it's charge times the flux. And the flux in this case is easy to calculate because that's almost a straight line. So that's just NV0 e to the EVF over KT. That goes into 0 over X sub B. And same thing for the holes being ejected from the base, and I'm going to draw that this way. JEP, EB. Okay, I got to label this one as E. This one is H, this holes. Now this is P E0 e to the EF over KT over X sub E. All right, and I'm going to try and make a long line here, because what I'm going to do, I always run up against this wall over here, is, I'm just looking to make sure you can see this. I'm going to define R. Now, I did do this in the notes, and this is a little bit not typical. R is not, I mean, usually defined in this analysis. And I'm just trying to make things a little bit simpler for you guys. So I'm going to define R as the ratio of these two. Now you sort of get the idea that, just jumping ahead, that for this thing to work well, I want this to be a lot bigger than that. And we'll get back to that in a minute. So I'm going to define this ratio as the ratio of the hole to the emitter current components. Now, you can see they both go with e to the EVF over KT, so that drops out. So just starting to do it, DH PE0 over XE over DE and B0 over X sub B. And I'm trying to be neat here. All right. So that's, all right. DH, I'll bring that XB up over DE and that XE down there. And now I'm going to write out PE0 and NB0. Okay, and you know how to do that. PE0 is the equilibrium hole concentration, so that's Ni squared over the emitter doping. And NB0 is Ni squared over the base doping. So then that's equal to DH XB N sub B over DE X sub E N sub E. My cat's trying to make an appearance again. Okay, so we've determined what the ratios are, and you kind of, if the diffusion coefficients are the same for holes and electrons, and the XB is equal to XE, it's just the ratio of the doping densities. And so what you see is that for this to be big, I want this, draw it really big, I want this to be doped really heavily with respect to this. So I want the to get this arrow to be bigger than that arrow, and of course that makes perfect sense, as we discussed in our last lecture, that if I want asymmetric current flow, if I want this one to be bigger, more electrons going that way, I dope the emitter more, because then there's more electrons to start with. Okay, so this sort of, it doesn't quite complete our picture. Let me put that in the wrong place. Put it over here. And it should be. Actually, maybe it's. Do it this way. There you go. So the emitter is doped more heavily than the base, and it gives rise to this being much bigger than that. And here is the actual ratio of that to that. And so you can see you can also make the ratio smaller by making XB smaller. All right, now I'm going to draw one more thing here, which is that these electrons flying across into the base, we want them to be collected. And so I'm going to draw an arrow here, and I'm going to write that as alpha JEN. Okay, and you can see that the idea is I want alpha to be as close to 1 as possible. And what happens is you lose a few electrons in the base. So alpha is something like 0.9 or something like that. All right, and that's really all we need for a basic first order analysis of a bipolar junction transistor. Now what we're going to do now is we're going to calculate what people are interested in most of the time, which is the current gain. So what I'm going to do is I'm going to label. Now I'm writing it as J, but again, let me just erase my picture. Remember that for each of the current components going between J and I, it's just a single. Don't do that. Single area A. So so that's the collector current. That's the base current. And now, this is what you always do. You define the base and collector currents as flowing into the device, and you define the emitter current as flowing out of the device. You could do it the other way, it's just that it makes it more convenient to calculate everything. And J sub E is the sum of these two. All right. And J sub C is just that one, because this is reverse biased. Now, for those of you that might have covered this in more detail in another class, I am neglecting some other current components. Which, for example, you know that a reverse bias junction does have a tiny bit of current going the other way, but we're just neglecting that. And so we're just treating that as the only component for now. So this is kind of a first order analysis. So then JC is just alpha JEN. All right. Now you may be wondering what's JB. Don't worry about it, okay? JB takes care of itself. We just have to know what JE and JE. So, this is very simple really, because, JE is the Hole electron of the forward bias base emitter junction, and JC is just this alpha you know, something close to 1 of JEN. All right, now, what we're most of the time interested in is beta, which is JC over JB. That's our current gain. I'll talk more about this in a little bit, but let's just proceed here. Now, okay, I said you didn't need to worry about JB. Okay, why? Because, all right, remember we have the Kirchhoff's law. Kirchhoff's law is that JB, let me write it out here. Okay, I'll first write out JE is JB plus JC, right? JB plus JC equals JE. So JB can simply be written as JE minus JC. And that's why I said you didn't need to worry about it, because I'm just going to write it in terms of the emitter and collector. So I don't, you know, need to worry about it. Now I just plug in alpha JEN over JEN plus JEP minus alpha JEN. And so you see I've written it in terms of these two components here. And then I'm just going to divide out. What I'm going to do is divide by JEN, so this becomes alpha over 1 plus JEP over JEN minus alpha. All right, I just divided by JEN. And so beta, just plugging in for there, it's just alpha over 1 plus R minus alpha. And that's it. That's how I want you to learn this for now. So, you know, understand these current components, 1, 2, 3, and how to calculate them, particularly the ratio of these two, and how to calculate beta, the current gain, JC over JB. Now what you see is that for alpha going to 1 and R going to 0, remember that's our perfect situation. Our perfect situation is this, the ratio of this to that goes to 0. That in that case, this becomes 1 over 1 plus 0 minus 1, infinity. So in order to get as high a current gain as possible, we want alpha to go to 1. Now what does that mean? That means we don't lose any of these electrons in the base. And we want R, the ratio of these two, to go to 0. And what does that mean? That means that the current component is across here is just this component here. So that's our perfect condition. But this is our result, where R is given over here. All right, now let's talk about what happens in a circuit. So I'm going to draw the circuit diagram for this transistor. So this is IC. And this is IE going out. And this is IB. All right. And this is VBE. And that's forward biased. And I'm just going to make up a new voltage here, the voltage between the collector and the emitter. And now we define VCB here, and I'll talk about that in a second, but in terms of using this device in a circuit, usually this is the voltage you're interested in. Now you can see that VCB is just the difference between this minus that. All right, now let's draw our current versus voltage. So we want IC versus VCE. And what we've derived basically is that it's a simple ratio. Now, remember, beta is JC over JB. But remember, and I erased my, my actual picture of the device. It's the same area for each current component. So this is IC over A, and this is IB over A. And so that's also equal to IC over IB. So IC is equal to beta IB. So what we do usually is we draw a family of curves for different IBs, and I'm going to just label them 1, 2, 3, I mean some arbitrary current, and then IC is just beta, 2 beta, 3 beta. And that's as far as we're going to go today. So we've gone as far as showing our I versus V for different IBs out here where VCE is high, so to speak. And I want you to sort of be aware. So you know when you forward bias a PN junction, VBE is going to be around 0.7 volts, right? That's roughly what it works out to be. And so for this all to work, this has to be reverse biased, which means this has to be a positive voltage. Now, that voltage again is VCE minus VBE. So this works, down to, somewhere around a volt. And then when VCE gets below a volt, because VBE has to stay, around 0.7. And so then we start to run in a situation where that's not reverse biased anymore, and then something else happens. And we'll go over that next time. This is called the active region of the transistor. That's where VCB is essentially positive, so that it's reverse biased. And next time we'll talk about what happens as you get closer here. Now, I just wanted to make one final remark in this lecture, which I remember when I first started learning about this device, it confused me. Because, and you might have had a circuit class where you use this transistor. By the way, I didn't complete this because this is NPN. And so the circuit diagram, you have an arrow there indicating that's from P to N. I remember when I first learned it, because, and if we start doing circuit analysis with this or designing circuits, we treat it as a current controlled current amplifier. I mean, basically, as I input a certain current and I get an amplified current here. And I remember, it just seemed like kind of a disconnect because we've analyzed this thing in terms of, okay, forward biasing the junction and seeing, we didn't talk about IB at all here, right? And so when you come over here and then you go, oh, all right, okay, so I'm going to put in a certain IB and then I'm going to get a certain IC, it seems like kind of a disconnect in the whole logic. That's not something to worry about at all, because it all fits together, meaning you can kind of think about, okay, you can kind of think about it that the device is really controlled by VBE, okay, that I forward bias it and then I get a certain, and it doesn't really matter, because if I really operated this thing with a current source here, IB, all right, it would have to be that that current source would somehow forward bias that junction and make that IB happen. It would have to be, right? Because these equations are all self-consistent and connected with each other. So the fact that you think of this as a controlled current source shouldn't worry you at all. Because it just means that if I want to get a certain IB by putting in a current source there, I have to have a certain VBE. It all has to work together. So even though we did the analysis, we didn't worry about IB at all, when it comes time to use the device, you can simply think of it as working this way. And so everything's fine. There's no reason to worry about that part of it. IB takes care of itself. All right. Now, okay, so we're going to finish there. Next time we'll talk about what happens here. We'll maybe, I don't know, we're not a circuits class, but maybe talk about it in the circuit a little bit, maybe, I don't know, and go from there. Now, what we're also going to do next time is we're going to address an issue with this device, which has been solved by sort of modern device fabrication, which is that in order for us to get high gain, we not only want the base doping to be small, but we also want the base thickness to be small. And that can lead to a certain problem when operating this device as a high-speed device. And I'll explain next time how that's fixed in modern electronics. Okay, that's it for today.